in a lesson 5, and in this lesson we're going to be working on applications or exponential functions. So some common places that you'll use, and this is not all of them by any means, but some common places that exponential functions are used are when you're dealing with compound interest, compounded continuously interest. So there's a difference there. Compound interest, you may compound it, X number of times a year, like quarterly, so 4 times, semi-annually, twice. Compounded continuously, it's an ongoing thing. So we do have different equations there, and we'll see what that looks like shortly. Also exponential growth and exponential decay. And with decay, we're going to be taking a look at half-life in terms of compounds. So as you can see, at least in these bottom 3 equations, they all have E. We use E as a natural base. So as I told you before, you'll see that a lot in your application type of problems, okay? Now, these formulas I do not expect you to memorize. I would provide them for you. You just need to know how to plug and solve. In most cases, we are going to be solving for a variable in an exponent, which is why we are doing this during this unit. We can plug in any number and solve for, our amount after t years, and just by typing that in, but it's going to be a little more interesting when we're solving for like the interest rate or the time, okay? So let's take a look. All right, so in problem number 1, it says, how long will it take for an investment of $2,000 to double in value if the interest rate is 7.25% per year compounded continuously? So when I see those words compounded continuously, I know I'm going to be using that formula. If it doesn't have the word continuously, it's just compounding interest, okay? So if I look at my compounded continuously formula, I've got A of t, meaning the amount after however many years, 5, 10, whatever our problem states, equals the principal times e to the interest rate and the number of years. So A equals PERT, pretty much like PERT plus the shampoo. Okay, so A is always going to be how much it ends up being after you've invested your money. So in this problem, it tells us my money will double. So if I'm investing $2,000 and I'm waiting for it to double, I'm saying how long it's going to take to get to $4,000. The principal is how much you are putting in to begin with, which was $2,000. My E is my base. The rate is 7.25%, but do keep in mind that when you're putting it into a problem, you need to change it to a decimal. Do the Beyonce, to the left. So it's 0.0725, and that t is what we're trying to find. After how many years will it get there? All right, so now we're just solving an exponential equation. So before we can take the log of both sides, because I highly doubt we're going to find a common base here, but before we can take that log, we have to isolate the exponential function, which is this part right here. Okay, so we need to get that alone. So what can we do? We can divide both sides by 2,000, which leaves me with 2 equals e to the 0.0725t. Now do keep in mind my variable is in the exponent. That's what I'm trying to solve. I need to bring that to ground level. This 0.0725, I can't move yet because it's stuck up there as well. So how do we bring it down? We take the log of both sides. You really can take any log base. However, because my base is e, it makes sense to do the natural log because they will undo each other. So I've got the log of 2 equals, I'm going to use my power property while taking the log, 0.0725t, natural log of e. Now guys, I'm trying to solve for t, so all I need to do is divide both sides by 0.0725 natural log of e. However, keep in mind, the reason I did this is because these two undo each other and it leaves me with just 1, right? Because really, natural log of e is saying log base e of e, and that's our base property. Log base 2 of 2 is 1, log base e of e is e, so the natural log of e is 1. This kind of just cancels each other out. They are inverses. All right, so really I'm just doing t equals the natural log of 2 over 0.0725. Now, if you didn't recognize this and you forgot, it's not the end of the world. If you typed in natural log of 2 divided by 0.0725 natural log of e, you'll get the same answer because this is just 1. So it's not going to affect your answer if you didn't recognize that. Okay? All right, so let's go ahead and type it in. Maybe you can turn on calculator. Thank you. Alpha y equals enter to get that fraction outline. It's going to help us. Natural log of 2 over 0.0725. And it will take about 9.5 years, okay? Here we can just round our answer to make sense, so about 9.5 years. If it asked me to round to the nearest years, I would say 10, not just because of rounding, but anything above 9 is going to be up to 10 because at 9 years I haven't reached it yet. Obviously in 10 years I've surpassed the goal, but we need to keep that in mind. All right, so the deer population grows exponentially. The current population is 125 deer. The growth rate is 16% per year. Find the number of years required for the deer population to be 400. All right, it's growing exponentially. So I'm using exponential growth, which is the same pretty much equation. Okay, I'm saying, what am I going to end up with? I'm ending up with 400 deer. I started with 125. E, my rate is 0.16 because I changed it to a decimal, and I'm trying to find the years. All right, so we're going to go ahead and solve. Divide both sides by 125, and we end up with 3.2. All right, now my variable is in my exponent, so let's go ahead. My exponential function is isolated. Let's take the log of both sides. So the natural log of 3.2 equals 0.16t, natural log of e. Okay, remember those undo each other because they are inverses. So I've just got t equals the natural log of 3.2 over 0.16. So we can type that into our handy dandy calculator. Let me get the natural log of 3.2 over 0.16. And that gives me about 7¼ years. Okay. All right, let's continue on. ASCII 946, I don't know what that is, has a decay rate of 3.5%, decay, exponential decay. If the original sample is 50 grams, how long will it take for it only 10 grams the sample to remain? So we're going to use our decay formula, okay, which is down here. Notice it's the same thing except I have a negative rate as opposed to a positive. All right, so I'm going to say, but keeping in mind that what I'm left with, what's on the left side of the equal sign should actually be the smaller number this time because it's decaying, it's going down. I have 50 E, my rate is negative 0.135. Okay, making sure I change that to a decimal. Trying to find T. All right, let's go ahead and let's do it. Divide both sides by 50. That leaves me with 0.2 or 1/5. Because it's a nice clean decimal, it might be easier to leave it as a decimal. All right, I got an exponential. Let's solve it. Let's take the log of both sides. Natural log of 0.2. Bring this down. Natural log of E. Inverses. So T is going to equal the natural log of 0.2 divided by negative 0.135. All right, when I type that in, I get about 11.92 years, so about 12-ish years. Okay. So if a 325 milligram sample of radioactive material decays to 195 milligrams in 72 hours, find the half-life. So half-life is saying how long will it take to become half of the life. So if you take 325 and divide it by 2, that's 162.5. So we have not gone through a full half-life cycle. So we're saying in 72 hours, it's gone down not quite a half. So we should expect our answer to be a little bit bigger, okay, in terms of hours. So we're going to use this formula. It's what I put on the front has some more involved in it. So we're going to use this, and I'll explain in a second. So it's a decay one. However, A of t is the amount over time. So like what are you left with? Just like in number 3, equals what we started with. Our base is going to be 2, and we're going to raise it to the negative t over h. Now you can also use this, which is the same thing, and I'll talk about why in a second. Thinking half-life, my base should be 1/2, right, to the t over h. T represents the time divided by the half-life kind of being how long it takes to get there. Now, these two are the same. The difference is I just rewrote this fraction. 1/2 is the same thing as 2 to the negative first. So I just figured it might be easier for some of you to do, to use a whole number as opposed to a fraction. But at the end of the day, it doesn't matter. You're plugging it into your equation. So we can use either of them. Just make sure if it's a base of 2, it's a negative t, all right? Because that's 2 to the negative first is the same as 1/2, right? Half-life. Okay, so we're saying we're going to end up with 195. We started with 325 times 2 to the negative t, so negative 72 over h. Okay, 72 hours. So, and this is an exponent. No, it doesn't super look like it, but that's an exponent. So our variable's in our exponent, but it's also in the denominator. So we'll deal with that later. We're going to solve it the same way. So I can do 195 divided by 325, which gives me 0.6 or 3/5. Okay, so we were 60% of the way done into our half-life. So I have 2 now to the negative 72 over h. Okay, so variable, my exponent is a variable, so I do need to take the log of both sides. So I've got the natural log of 0.6 equals negative 72 over h times the natural log of 2. Now my variable is down to ground level now because of the power property, but it's in the denominator. I don't want my variable in the denominator, so I'm going to clear it out. I'm going to multiply both sides by h. Give me h times the natural log of 0.6. Okay, when I multiplied over here by h, just cancel that. Natural log of 2. Okay, so now I can just go ahead and do it. H equals negative 72 natural log of 2 over the natural log of 6. All right, type it into your calculator. Boop, 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 boop. We get 97.7 hours, which makes sense. Okay, we were at 72 hours. It was about it was 60% of the way done. So going from there. All right, our last two are dealing with just compounded interest, not compounding continuously, just interest. All right, so if $2,500 was invested 6 years ago and the interest was compounded quarterly, what was the interest rate if the current value is 3,425? So we're saying compounded quarterly, that's 4 times. So when we take a look at our formula over here, okay, we're saying how much we ended up with, how much we invested, R is the rate, N is how many times per year, and T is the total number of years that you're doing your compounding. Okay, so I'm just going to jot that down right here so we have it, and you guys have something to look at. A of T, the amount of time, the principal times 1 plus the ratio divided by how many times we compounded, number of times compounded times the time. Okay, so in this case, we are solving for the rate. Always look and determine what you're solving for, okay? So we're starting with this. I'm sorry, that's what we ended up with. We started with 2,500. We don't know R. We're compounding 4 times because it said quarterly to the 4 times 6. So guys, in this case, if you notice, where is our variable? Is it in an exponent? No, it's not. We do have an exponent in our problem, but I'm not asking you to solve for it. Okay, I'm solving for R. So the only time we're going to take a log of both sides is if the variable's in the exponent. That's how we bring it back down to the ground. So don't always think just because you have an exponent now it's going to be, oh, I'm solving by using logs. That's only when the X or the T or the P or the whatever is the exponent. So we'll deal with that. We're trying to solve for R. So let's undo. Divide both sides by 2,500. This ends up being 1.37. It ends up being an actual clean decimal, which is kind of weird, but so we'll keep it as that. Now let's think about this, okay? I need to undo that exponent. It's not a variable, so what's the opposite of raising something to a 24th power? It's 24th, taking the 24th root of it. So I'm not going to type that in yet because we've seen how in exponential problems, even just rounding a smidge can completely throw off our answer. So I'm just going to leave it as a 24th root of 1.37 and actually type it in a little bit. Okay, so that's done. I did the inverse. All right, so now what? Let's subtract the 1. So I'm just solving for R here. So I've got the 24th root minus 1. And my last step to get rid of R, or to get R alone, is to multiply by 4. So I end up with 4 times this. And this is not something I expect you to actually calculate by hand, but we can type it in. But just to be as clear as possible and as close to the answer as possible, I haven't really done much yet. Okay, so 4. Now, to do the root, go to your math menu. Do you see option number 5 right here that has the X in front? That's telling you you can put in any index you want to. Oh, oops. Sorry. So I typed the 4 first, so it made it the 4, so I can do 4 parentheses because I do need parentheses there. So you can type the 24 in first and then go and do that. Or you can just pick option number 5 and then go back and put the 24 in front of it. It will leave a little box there and let you type that in. Either way. And then just make sure you arrow out of that before you do the minus 1. All right, so we get 0.0528. That's a really small percent. But remember, when we put something into our equation, we put it as a decimal. So to change that to a percent, it's actually 5.28%, okay, which makes a little bit more sense. All right, in the last problem, we are using the same formula. It's just compounding. This one says compounded monthly. So how many times am I compounding in a year if I'm compounding monthly? 12, yes, because there's 12 months in a year. Okay, so we invested 2,500, we ended up with 7,500. The rate is 0.065 divided by 12 to the 12 times t. Now, you can go ahead and do the 1 plus 0.065 divided by 12. However, remember, I'm going to leave it like that and just calculate it all at the end. Since we can pull up the fraction outline in our calculators now, it makes things a lot easier, and my answer will be as precise as possible, okay? If I type it in now and round and stuff, I could potentially, and my last class saw that actually happen, I could be very far off with my answers. All right, so let's solve an exponential. This time I will take the log of both sides when I get there because the variable is in the exponent. So divide both sides by 2,500, gives me 3. All right, now what can I do? Bring that exponent down to the ground. So I'm going to take the log of both sides. So the natural log of 3 equals 12t times the natural log of all this stuff. Remember, this is just a number. 1 plus 0.065 divided by 12 is a number. If I take the log of it, it's a number. Okay, so don't overthink that, and because it looks messy, I'm just leaving it. I just haven't calculated yet, so I can get, like we said, the closest answer. So I've got 12 times some number times some number. Well, I'm solving for 12, so we can divide by these first two things. So I've got the natural log of 3 divided by 12 times the natural log of 1 plus all this. And I can just type that into my handy dandy calculator to get my answer. So let's go ahead and do that. Okay, so I want to pull up a fraction outline. All right, so the natural log of 3 is in my numerator. In my denominator, I've got 12 times the natural log of 1 plus another fraction. So pull up another fraction outline. You can put as many fractions in a fraction as you want to on here. 0.065. The nice thing is you don't have to worry about making sure you have parentheses in the right spots, in case you make a human error when you type it in. The calculator is only as smart as you tell it to be. If you type something in wrong, it will give you the correct answer for the wrong problem. All right, so about just shy of 17 years. All right, so a lot of these applications, guys, is just plugging in and solving an exponential equation, okay? Once again, you don't need to memorize the formulas, but you do need to know, what to plug in where and how to solve for when you have a variable as your exponent. All right, and we are done.